Hello, everyone. Today we're going to talk about a topic that I feel like should be discussed more in a linear algebra course or maybe a Calc 3 course. And is why are these. I'm assuming you have a background and you know what an inner product and an outer product is, but you just don't know why they're called inner and outer products. And it is because the definition of inner and outer product has another definition in a summation form, and I will show that today. So let's start with inner product. What is an inner product? Usually, it's denoted. It's all sometimes called a dot product. So if you have vector A and vector B, it would be denoted by a dot product. It can also be denoted by these brackets here, these triangle-looking brackets, and it's also um, denoted like this: A transpose B for the matrix multiplication kind of rule. And what does it say? So let's say our vector A looks like something like 1, 2, 3. Those are the elements, 3 elements in our vector, and vector B is 4, 5, 6. Okay. What do these three notations mean? Well, if you know anything about matrix multiplication, this A transpose looks like this. Let me space it out a little bit better. Okay, that means you're multiplying this this row vector with this column vector. And when we do this, we're basically multiplying each element of these vectors one at a time with each other. So like the first element here corresponds to this element corresponds to this element, and we multiply it like that. So we get 4 times 1, or actually let's say 1 times 4 plus, and we're denoting with plus, okay? 2 times 5 plus 3 times 6. This is 4, this is 10, this is 18. So this is 22. If I do my math correct, this is 4, this is 10, this is 18. Okay? So that is a dot product. But let's think about it. Let's just think about it for a second, okay? How can we write this in a different way so we can explain why it's called an inner product? Well, what are you doing here? We're adding and we're multiplying two things. So what do we write when we have a summation? We have a summation. How many times are we summing? Well, we're summing it twice, but we have 3 elements. So we're summing from, I'm going to say I is the index, from 1 to 3. And then what are we multiplying together? We're multiplying A, the vector A, at I, times B, vector B, at element I. So this is inner product in summation form. Now, I was never taught this at any linear algebra class or any mathematics class I took. So it really shocked me to see that people don't know this because, or they don't teach this, because this is like fundamentals. Like if you want this to turn into a matrix, this is a way to turn summation into a vector, into a matrix, into a scalar, whatever you want. But in this case, this is a scalar. Oh, sorry. Let me write this in a clear way. So what are we doing here? This is the inner product. Inner. That's why it's called inner product. Okay? So if we take this notation here, this notation, this equals this notation. Okay? And of course you can generalize it more. Instead of having 3 elements, we could have n elements. Of course, so that's what we're doing. Now, why is it called an outer product? What is an outer product? Well, look at this. If this is an inner product, then it follows naturally that, well, we have two terms here. Maybe we have a double product on the outside. We squared this summation part here. We squared this part. We squared this part. Okay? So we have summation AI and summation, I'm going to put J here from 1 to 3 of Bj. Okay? So this is the outer product. Okay? Because, do you see it? This is the inner product because we're talking about inside the summation. But when we're squaring the summation, it becomes an outer product. That is why it's called an outer product. Okay? Now, we all know that this can also be written as A, B transpose. Right? So we have an A vector, a column vector. Let's say it's 1, 2, 3 again. But this time we have a B transpose. So this is a row vector. 1, 2, okay. 4, 5, 6, right? Okay? Now, and what does this equal? This equals a matrix. Because what does this turn into? We all know the outer product makes a matrix, but if you think about it in the summation terms, we have two summations. We can combine them like so. AI Bj. Okay? So what are we doing here? This is how I like to see it. I was never taught how to read a double summation, but this is how I do it, okay? First, let's set up a matrix here. So we have first iterate this one time. So plug in A1. So A1 is 1, as we can see right here. A1 is 1. So we got 1 times, plug in J. J1 is 4. 1 times 4. But we're keeping the I, and we're iterating the J. So then we go 1 times, what's the next? 5, 1 times 5, 1 times 6. Now we're done iterating through the J, and we got to reset the summation. Resetting this summation creates a new row in this matrix. Okay? It creates a new row. Okay, so we iterate we iterate I again. So we got 2 times 4, 2 times 5, 2 times 6. Iterate again, new row. 3 times 4, 3 times 5, 3 times 6. Okay? This creates a matrix. Okay? And you can further reduce this down into what it is, which is this. All right? It creates a matrix. So that's why it's called an outer product. What happens to make it even more clear, okay? Let's make, instead of A and B vectors, let's make an A vector just A. Actually, let's make it U. U vector, okay? U vector dot U. Or U vector like this, like an inner product, or U vector transpose U vector, okay? So we know from our notation up here that it should equal this. It should equal this, okay? So we have summation I equals 1 to n ui vector times ui vector. What is that? These two can be combined. So this can be I equals 1 to n u vector squared. Inner product. It's on the inside of the parentheses. It's on the inside of the summation. Okay? Now what's an outer product? Well, I keep wanting to spell outer product with 2 I's. An outer product is we went with u transpose. But in summation terms, it is summation I equals. I'm gonna explain this in a second. I'm gonna put k. K equals 1 to n. U I vector all quantity squared. And now what happens when you square a summation? Square a summation is double summation. That's just an algebra. I didn't learn that anywhere in algebra, but that's something that you got to know. So this becomes, you got to change to the index. That's why I changed it from k. So you got to do I equals 1 to n, j equals 1 to n, u I, u j. That's what this becomes. Okay? But back to my point, why are they called inner and outer products? It's because in summation form, you're taking the inner product. But when you're coming to the outer product, you're taking the outside, the whole summation, and squaring it. But you're taking the inside of the summation and squaring it. That's an inner product. I just thought that would be interesting to know. And I'm going to do one example for you guys that really cement this. It's transition. I was never taught how to write these products in terms of summations. So I'm a statistics, my focus of research and study is statistics. So a common problem in statistics is called the least squares problem. Now, I'm not going to go into the details because that's for another video, and you can look that up on YouTube. We get to a point in the derivation of the least squares problem. It looks like this. Oops, let me make a handwriting look a little nicer. Okay, j equals 1 to p xij j squared. So basically, this is one part of the least squares. You don't have to know the background of the least squares for this example. But my question right now, with using the properties of inner product and outer product, can we translate this term into matrix or vector notation just from summations? How can we do this? Well, let me just make sure we understand what we're working with here. This is I believe this is a constant. This is a constant. It's unknown. This is a vector. Well, actually, let's be more clear. This bj with the summation is a vector, okay? Xij, let's come back to that. Yi is a vector. It's an n by 1 vector because it gets iterated by this summation. Now I'm gonna clean this up a little bit. I'm gonna clean this up, get rid of my notation. What do we see here? We have a summation and we have a quantity squared. Okay? Refer back to, is this square right here? Is this square squaring over the summation, or is it squaring over the inside part of the summation? The answer is that it's squaring the inside part of the summation. If it was on the outside, it would look something like this. It would be like this. Okay? But it's on the inside. So what does that say? That means it's an inner product. It's an inner product. So this whole piece here is an inner product. Okay? Now let's work inside. What do we have on the inside here? So we have, let's work on this xij here. Okay? So this xij is iterating over two summations, this one and this one. Okay? It's being iterated over two summations. And what do we know about two summations? Double summation. Let me write this in another way. Double summation is summation squared, basically. Okay? This can be written as a double summation. So this is an outer product. Oops. What do we know about outer products? Outer products make a matrix. So this is an X. I'm going to bold it. Actually, I'm going to set my stylus pen to a different... this is X. Bolded X. Bolded X for denoting as a matrix. Okay? And now, this, and this combine to a vector. You just add an element to a vector. Okay? And then this becomes a vector. So how can we write this? Well, let's write, what should the inside piece be? We know it's an inner product on the outside, but what should the inside of the inner product be? Well, we have a y, right? This is a y vector. I'm going to make that clear. That's a y vector minus an X matrix, okay? Then times B, which is a vector. It's a vector. Transpose y vector minus X beta. Okay? That's the matrix or the vector matrix notation for it. I hope that makes things a little bit more clear, and I really wish they taught this more in linear algebra class, and because I use it quite a bit in statistics now, and it's like it's hard to teach myself this just straight out of the bat. So I just thought I'd make a video on it. But that is why it's called an inner and outer product. I didn't realize that until I did the summation versions of vectors and multiplying vectors, multiplying summations, and stuff like that. So hopefully that you found that entertaining or informative. And so I will see you guys later.